started. So we come to the next speaker and similar program, application of material forces in path independent integral for prediction, track initiation and track passes. Contribution comes from the University of Kassel in Germany. The speaker is Dr. Paul Gilles.
Okay, thank you very much, Mr. Chairman. So, the title of my talk is Application of Material Forces and Path-Independent Integrals for the Prediction of Crack Initiation and Crack Paths. So, this is the outline of my talk. I will start with a short motivation and present a short theoretical introduction into the topic, and I'll explain how we perform the crack tip loading analysis and how the crack initiation works in our model. And then I'll present some numerical and some experimental crack paths, and finally, in the end, I'll draw some conclusions. So this is a flow chart of crack propagation simulation. So the very important topic is, of course, crack loading analysis or crack initiation analysis if you don't have cracks or if new cracks arise. In our model, we use the commercial code Abacus for solving the boundary nullity problem, and we use a remeasurement algorithm. So I'll mainly focus on this part here in the following slides. So for performing crack tip loading analysis, one can use different methods. For example, one can use special crack tip elements. We apply path-independent integrals, and namely we use the J integral here. So one can use a small integration contour as shown here. This, if one does this, one can run into problems as soon as the crack approaches internal boundaries, like this hole here. Then you have to choose very small integration contours, and then you are within the region of the numerical inaccuracy of the finite element solution. And therefore, we choose very large integration contours far from the crack tip, close to the external boundary of the problem. But then, to obtain path independence, one has to consider additional integrals along such a hole or an interface, and also along the crack faces. Okay, one can derive balance equations in the material space by applying, for example, the gradient operator to the Lagrangian function. Then one obtains that the divergence of Shelby's energy momentum tensor vanishes. Furthermore, we can define a material traction vector, which we use later, and in the end we obtain the balance of linear momentum in the material space. Müller and co-workers introduced a method for calculating local material forces, considering finite element framework. We have the weak form of the problem. Then we apply the isoparametric concept for interpolating field variables on finite element, and we end up with this formula for calculating material forces or the contribution to of the force to one node at one finite element. And to obtain finally, well, of course we may have several finite elements connected to this node. So each finite element brings you a contribution to the resulting material force here. And if this node represents a volume that is defect-free, then of course the material forces vanishes, as the equilibrium holds true. Furthermore, if we have a crack at this position, then we have a defect in the material space, and what we obtain is a resulting material force, which is related to the crack driving force, and is exactly the negative value of the J integral. Other than this local approach, one can also apply an integral calculation for calculating material forces. For example, one can use an integration path along, for example, element edges, So one obtains material forces acting or resulting from these integrations, and of course, as this volume is defect-free or is defect-free, then again our equilibrium holds and sum of these forces is equal to 0. Same holds if we have more finite elements, and again, if we have a crack, then we need to consider the integration along the crack faces as well. But we cannot capture with this integration material force at the crack tip. Therefore, what results here is the crack driving force, which is nothing else than a J integral, and this is what we use in the following. So, as I said before, we do not apply small integration contours, we choose such large integration contours, and as there are maybe other defects in our material or in our boundary value problems, for example this hole, there also are material forces present. Therefore, we need these additional integrals to separate the crack driving force from these forces and these other defects like interfaces or also crack faces or these internal boundaries. Furthermore, one runs into problems as soon as the integration approaches the crack tip, and we have this region delta where numerical values are inaccurate, and therefore one needs some special numerical treatment to accurately calculate, especially the second coordinate of the J2. Furthermore, we are interested in where do cracks initiate. Therefore, we had a look at material forces at stress concentrations. For example, a hole, notch, or sharp notch, or at the end we have the crack. You can load it with a tensile loading or tensile and shear loading, and this is what the material forces look like. In the next slide, I will focus on these two cases. So let's have a look at a circular hole and the distribution of the material forces. As the local calculation of the material forces or calculation of the material forces is mesh dependent, and therefore we use this QK, this material force density or material traction vector to obtain a mesh independent quantity. If we plot now the material forces, here we have the local and the integral calculation along the surface of the hole, then we obtain this plot. And if we compare it to the maximum principal stresses, then we see that the maximum is identical. Furthermore, we can have a look at such a specimen with a notch which may be inclined. And there were some experiments at this specimen. And if we now, and we also had a look at the material tractions along this surface of this U-shaped notch, and we see that if we assume that crack initiates into that direction where the material force is maximum, then we see that the experimental deflection angle and the angle predicted by this approach is nearly identical. Furthermore, we also calculated an average energy release rate applying coherence theory. So we calculated the work done by the externally applied loading, and we calculated this for the case where we only have a notch and no crack, and then we have a crack assumed that the crack initiates into arbitrary directions. So we can plot this also along the surface, and we see that also the maximum of this average energy release rate and the maximum of the material force approach is identical. Okay, finally, I want to show you some results of crack path predictions applying this model. So here we have such a specimen, a CT specimen. The specimen is made of is a composite specimen. The matrix material is polypropylene, and we have glass and cellulose fibers as reinforcements. The specimens were cut out of plates. These plates were manufactured applying an injection molding process. So we have a certain flow direction, And this is the flow front, and one can think that, or it's clear that fibers will mainly or predominantly orient parallel to this flow front. Therefore, we can expect that there will be also a predominant direction of fracture. And we performed CT tests and measured this critical J integral values. And we see that if the notch is perpendicular to this, or is parallel to this flow direction, then we obtain a respective large value. And if the notch is perpendicular to the flow direction, then we obtain a small value. And if you define this anisotropy ratio, this is for the cellulose fibers is larger than in the case of the glass fibers. So we use these values in our model. We use an interpolation function, an elliptic interpolation function, to define this material colorimeter as a function of the orientation. Furthermore, we have the J integral. Also, you can write down also as resulting as function of the orientation. And we assume now in our model that the crack grows into that direction where this ratio is a maximum. Okay, here is the case of beta equal 0 degree, and beta is the angle between the ligament and the predominant direction of fracture, which is parallel to the fibers, or the predominant direction of fibers. We considered two different types of the fibers. So we have one homogeneous assumption. So in this case, we have fibers always in the whole specimen parallel to this initial notch. And we have the heterogeneous fibers assumption. Here we assume that the fibers are always parallel to the flow front. And furthermore, we have the experimental results here. And we see that in the case of the homogeneous fiber orientation, we have straight crack paths for both fiber types. So in the case of cellulose fibers and glass fibers. And if we choose this, or if we assume this heterogeneous fiber orientation, then we have a slight crack reflection, and it's also in the cellulose fiber types. And we see that the experimental results are in between both of these assumptions. So the more interesting case is, of course, the 90-degree specimen. Here we have the glass fibers. Here the fibers are now perpendicular to the initial notch. And here we see that this relation predicts a straight crack path, or in the case of heterogeneous fiber orientation, a very slight crack deflection. And this is also what we would have expected, because the CT specimen is one loaded specimen. If we now have a look at the higher anisotropy ratio, we see that we have a strong and immediate crack deflection. And this is also represented by our model. And again, we see that the experiment is in between these two assumptions. So with this model, we can catch such effects very well. Okay, finally, we come to summary and conclusion. I've shown you that the material forces acting at the crack tips represent the crack driving force and provides us information about the direction where the crack will go. Furthermore, we applied the path-independent integral to calculate accurately the loading quantities at cracks for arbitrarily shaped cracks, and also material homogeneities in volume. Fourth, then I presented you an approach for finding the position and direction of crack initiation, applying this material forces approach. What of course remains open is the question of the threshold value for incremental crack formation delta A. And in the end, I showed you also some crack paths calculated in a fiber reinforced polypropylene specimen, and we compared the experimental paths to our numerical paths, and they were in very good agreement. So thank you very much for your attention.
Thank you very much.
To you, and we are exactly in time. I'm really